Ace. Okay, so what we're going to look at today is electron configuration. So this is sort of, last week we looked at atomic structure and atomic history. So that sort of whole idea of sort of what we already knew about an atom from GCSE, that whole electron, proton, neutron idea, looked a little bit at isotopes, and looked at relative atomic mass and atomic mass, so how we work those out. We also looked at mass spectrometry, which was just basically looking at how different compounds are made up of different elements and how we split them up. Now we're going to look at electron configuration. Electron configuration is just the layout of where our electrons are in our atom, which is great. Unfortunately, what we've done a lot of GCSE said, oh yeah, we have 2 electrons in this energy shell, we have 8 in this one, 8 in this one, and that's it. And what we've done is, it's not that it's untrue, but we've just simplified it because it gets a little bit more complicated. And you'll see as I start to talk through this today, I'll start saying, oh, there's also this bit and that bit. I'm telling you that they exist, but I won't go into any more detail because we don't cover them at A level. They're sort of, they're then degree level, and the atom can actually get very, very complicated very, very quickly. So what we do is we just simplify it to the level that people need when they're learning it. And then when they learn the next level of it, we just add a bit more information and a little bit more description to how it's actually laid out. So what you've learned isn't untrue, it's just not the full picture. So electrons, this is what you're probably quite used to seeing. We've got an electron, we've got a nucleus in the middle, which will hold all of the protons and all of the neutrons. And we have these electrons that orbit the outer areas of our atom around the nucleus. So that's what you've been told in the past. Electrons are arranged in these shells around the nucleus. And you'll have probably been told on the understanding that first shell can have 2 electrons, second shell can have 8 electrons, third shell can have 8 electrons. It's not untrue, but actually, rather than using the word shells now, we start to use subshells and orbitals, because actually these shells that we've talked about in the past, these are actually just energy levels. So we're starting to get a bit more electromagneticity in here, electrochemistry in. So actually, this first shell, rather than being the first shell of on the electron, this is actually the first energy level. And this one here would be our second energy level. And then this one will be our third energy level. So that's actually what's happening here. These are energy levels. We do still have subshells. So we have energy levels. On each energy level, we have subshells and we have orbitals. So that's the first thing, is these original shells are now actually energy levels. And so they each have a different energy. So we have to have a little look at quantum theory. Now, we mentioned quantum theory a little bit last Monday, and it's this idea that electrons contain energy. Quite a basic idea of this principle, but we spoke about last week, actually, this idea with quantum theory is that electrons have a negative charge and our nucleus has this positive charge. Because our neutrons have no overall charge. And what would actually happen is, because positives and negatives attract, is an atom itself would actually compound in on itself and actually bring itself inwards, and almost like a black hole, really, because the way that the negative electrons and the positive nucleus will react is they'll want to attract to each other. So these electrons that are held in these outer shells, which have all these space around them, they couldn't actually just be held there by the normal forces of attraction, because actually they'd pull in together and it would all just sort of collapse in on itself. So this is where quantum theory came in, because we went, okay, electrons contain energy. And what we call this energy is in packets that we call quanta, hence quantum theory. And electrons are only stable when they have a particular multiple of energy, which happens to correspond to those shells. So those shells I've had here, where we said, oh, we've got energy shell level 1, we've got energy level 2, energy level 3. Our electrons are nice and stable, and they will stay on each of their energy levels. They'll actually stay on those subshells. in those areas because their energy level matches with the shell. So if they need energy level 1, they'll stay where the shell 1 is, 2 and 3. Electrons can change energy levels. So what we've classed as shells in the past. So what we've learned is shells at GCSE, I'll sort of put in brackets, and they're now energy levels. So they can change energy levels, but they have to step up or down to the next level. They're not allowed in between. So they actually either have to go the whole way up to the next level or the whole way down. And that's something that we'll look at a bit later on. It's not sort of something to worry about too much now, but it has to go all the way up or all the way down. It sort of can't skip in between. And what you'll find out, what I mean about this skipping in between, is actually these energy levels that we used to refer to as shells aren't actually these nice plain circles that we have around the outside. We actually have subshells. And in these subshells, we have orbitals. And so they would actually have to do lots of these mini jumps. So basically what we're saying is we can't go from somewhere on energy level 1 to another part of energy level 1. It's going to go from energy level 1 to energy level 2, or from 3 down to 2. So quantum theory again, the shells or energy levels are numbered, like I've said, and they have this principal quantum number, which corresponds to the period. And what we mean by that is, you've probably noticed in the past that an atom that has a electron has a certain amount of electrons, they finish in energy at third electron shell corresponds to the specific period of the periodic table. For instance, would be in period 3 of the periodic table. If they finish on shell 2, which is now energy level 2, it would be in the second period of periodic table. So for example, if we used helium as an example, helium's only got electrons in energy level 1, it's in period 1. So our smallest energy level next to the nucleus is 1, and that can contain up to 2 electrons. So that bit is actually the same as what we've spoken about at GCSE. We're just going on an energy level now rather than a shell, but actually it's the same thing. Energy level 1, that first shell from GCSE, is next to the nucleus, has the smallest energy, and it can hold up to 2 electrons. Energy level 2 can contain up to 8 electrons. So you can see here the links between GCSE and A level. It's almost like we've just changed the wording for it. We're saying, okay, energy level 1, it can hold this shell, this energy level now can hold 2 electrons. Energy level 2, that one is able to hold 8 electrons. And that's actually no different information from what you've been told at GCSE, apart from the fact we're using word level. Apart from this, then we get energy level 3. We go, energy level 3, that can hold 18 electrons. So this is where we start deviating a bit and we start looking into it a bit more. So that's our first change really here, is that, oh, my number 8's gone a bit strange. Our energy level 3 can contain up to 18 electrons. So that's our first biggest change here. So what we're going to look at then is these energy levels and how they work. So I'm just going to look at them in a bit more detail here. So what I've got here is N being representing our energy level. So N1, N2, N3, N4, N5, and so on. So as you can see, the energy levels get closer together as we move further from the nucleus. So the gaps between them are getting a lot smaller. Our lowest energy level is energy level 1. And N equals, and that is our infinity number, would be, it just keeps going. So this process would, hypothetically, if an electron, if atoms could keep growing to an infinite size, this whole same process would happen exactly the same. It would keep going and going. So electron shells, yeah, this is where we're going to start. It starts getting a little bit complicated. So what you will start to see in textbooks and revision guides is, unfortunately, interchangeably in places, we use the words energy shell an energy level, which is really not helpful in the slightest. So electrons orbit the central nucleus, and here we've got it saying in shells, and I've done this on purpose because what ends up happening is you'll read one book and it'll say in energy levels, you'll read another book and it'll say shells. So what I'm going to do here is I'm going to put shells, and I'm actually going to write next to it energy levels. It's the same thing. We sometimes call them energy levels instead, because then in a minute we're going to have subshells. So some people like to just have two completely different words. But obviously, if you're having a subshell, that means it's a smaller part of the shell. So then some people like to use shell and subshell, but it doesn't really matter. They're the same thing. So electron shells, electron energy levels, we're talking about the same sort of thing. Each of the energy levels goes up: first shell, second shell, third shell, fourth shell, so on. So electrons orbit the central nucleus in shells in energy levels. Each shell has an energy level assigned to it. And each shell can hold a different number of electrons. So the same as what we've just spoken about there. So each shell can hold 2n squared electrons. So n is our principal quantum number. So for example, the principal quantum number will be if it's energy level 1, 2, 3, or 4. And that is this shell number or the energy level number. So it's interchangeable, it's the same. So for example, our number of electrons that first shell can hold is 2. The number of electrons as largest amount of electrons that second energy shell can hold is 8, third is 18, fourth is 32. So this again is where we're starting to see a slight change now from GCSE, where we were going, oh yeah, it's 288. So that's our first biggest change. So let me get rid of that bit of typing. So atomic orbitals and subshells. What starts to happen here is electron shells are made up of atomic orbitals. So this is something new. We haven't really spoken about orbitals before. And these are regions in space where electrons may be found. So what we've really spoken about before is we've basically drawn an electron like this, and we've got an atom like this, and we've gone, okay, it's got an electron on here, it's got an electron here, got an electron here and here. We've just drawn them as little crosses. In reality, these circles that we're drawing as these shells don't actually exist. They're an energy level, they're an orbital, they're not actually a solid thing. They're not like the rings of Saturn. So we have these orbitals, which are parts of these shells. So atomic orbitals. So electron shells are made up of atomic orbitals. And so what these are these regions in space, so regions of these shells where these electrons may be found. So in specific areas of these energy levels, we are more likely to find the electrons in certain areas. So each energy shell, each energy level is composed of one or more orbital. Okay, so this is where it starts to get a little bit more complex. So actually, we don't just have these two electrons orbiting around the nucleus on this circle that we've drawn. Actually, we've got little orbitals inside this shell. So each orbital can hold one pair of electrons. Electrons can be held in pairs. Electrons, because of something called spin, which we'll look at in a minute, electrons cannot be held in groups of more than 2. They're always held in pairs, either singularly by their own or in a pair. And we can have 4 types of orbital. In reality, all you need to actually really know about is our s orbitals, p orbitals. We don't actually really do much with d orbitals at A level, and we definitely don't do anything with f orbitals. I'll have a little talk through them, but it's s and p that are our important ones. And so basically what these are is, if we sort of think of it like this, if we draw out a nucleus in the middle, and we put in a shell here, so this is our first energy shell. This isn't the ramp that it follows, and actually what you will find is somewhere else on here you would have an s orbital, and then you'd have another energy shell, and on that energy shell you'll find maybe, if we went energy level 2, we might find an s orbital over here, we might find a p orbital over here, another p orbital. And I'll explain the different types of orbitals now. We'll start off with s orbitals. Oh, sorry. So there's also this. Each orbital has its own 3D shape. And we call these an electron cloud. What you're going to see, you're going to see these pictures that we use in chemistry to show these electron orbitals. And they have clear boundaries. And so I'll just skip ahead. And so, for example, this is our s orbital. It's got a really, really clear boundary. It's really, really spherical, really clear. But they don't. In reality, they have fuzzy edges. And what we mean by this orbital is it's not an object. This is the shape. This is the area that the electron can travel around in and move around in on that energy level. So on that first shell, we have an s orbital, which is this circular shape here. And that circular shape is actually the places where the electron can move. Okay, so this circle doesn't really exist. So if we took a snapshot of this image, what you'd actually see is fuzzy edges because you'd see where that electron is moving around. So s orbital is able to hold up to 2 electrons. Okay, the probability of finding our electron in an s orbital is highest near the center. We've only got 2 electrons in here, so if we were to look at it nearest to be the center, 1s is smaller than the 2s orbital. So as we go up energy levels or energy shells, so first, second, third, fourth, the orbitals also become slightly larger for the s orbital. So 1s orbital is slightly smaller than our 2s orbital. And basically what this means is somewhere inside this spherical shape, we will be having electrons moving, and it is an electron cloud. It is not a solid shape. So that's really, really important to sort of grasp. So then we have our p orbitals. These have a 3D dumbbell shape. And these, again, as we said before, electron orbitals can only hold up to 2 electrons each. But our p orbitals always come in groups of 3, known as px, py, and pz. So whilst each p orbital can only hold 2 electrons each, because our p orbitals always come in groups of 3, we'd say our p orbital in total can hold up to 6 electrons. So px can hold 2, pz can hold 2, and py can hold 2. So we say in total they can hold up to 6 electrons, because actually they all have the same energy. So whilst it's px, y, and z, they all have the same energy. They're all at the same energy level. They have more energy than higher energy level than s orbitals, but actually there is no difference between x, y, and z p orbitals, apart from we've just got 3 separate ones, because they can only hold 2 electrons each. And in total, if we class them as a whole, the whole p orbitals per each energy level can hold up to 6 electrons. And then we have d orbitals. You don't actually need to know much about d orbitals. I've literally just put a picture up on there for you to have a look at them, and you don't actually need to know these. They have a complex shape, is all you need to know. They still only hold up to 2 electrons each, but d orbitals come in groups of 5. Groups of 5 are the same energy, so they can hold a total of 10 electrons. So you're starting to see the similarity here between the p and the d orbitals. P comes in groups of 3, can hold up to 6 electrons together. D comes in groups of 5, so you can hold up to 10 electrons. And our final orbital are f orbitals. And these, again, still only hold 2 electrons each. These have an even more complex structure, and these are only found in groups of 7. So in total, they can hold up to 14 electrons as an f orbital cluster. These are not covered at A level at all, so we don't worry about f orbitals. We mention that they exist, but it's sort of, here's an f orbital. They are the highest energy level of orbitals, and that's it. We don't have to worry about them any more than that. So shells and orbitals. this is where we start to break it down. So within each shell, so if I draw a shell on here, let's say we draw, here's my nucleus. So here's our first shell. That's our energy shell, energy level 1. So within each shell, orbitals that are the same energy level are grouped together in subshells. So energy level 1, shell 1, we already know shell 1 can only hold 2 electrons. So it's only made up of s orbitals. So energy level 1 will have an s orbital, and we know it can only hold a total of 2. Energy level 2, shell 2, can have s and p orbitals on there. Now we group them together. So what we mean by this subshell grouping is, rather than having to go px, py, pz, we're actually just saying 2p. So 1s means energy level 1, s orbital. If it was a 2s, we're then talking about energy level or shell 2, s orbitals, and that's their subshell. We can then also group all the p orbitals and call them 2p. So rather than having px, py, pz, we can just say, oh yeah, 2p. So 2p can hold a total of 6 electrons. 2s can hold a total of 2 electrons. So together, this energy shell, so energy shell 2 can hold a total of 8 electrons. And then the same thing happens again. We go on to shell 3, and we have a 3s subshell, which is made up of our s orbitals. We have a 3p subshell made up of our 3p orbitals, and then we get our 3d subshell, and that is made up of the 5 different subshells, 5 different d orbitals. So together, the third energy level can have up to 18 electrons, as the s orbital subshell has 2, the p subshell can have up to 6, and I didn't want that there actually, and that's the third. And then our d orbital, our d subshell, can hold up to 10. So you can start to see how they build on each other each time. So that's sort of the basics of how we split up into subshells, orbitals, shells. So subshells are just an easier way of us categorizing a group of orbitals, so we stick them all together in a subshell. So I mentioned spin before, and I said that electrons always come in pairs. So we're going to have a little bit more of a look about this thing now. So electrons have an intrinsic property called spin. And what spin is it's caused by our electrons. So if we have, I've said electrons come in pairs. So when electrons come in pairs, they're 2 particles that both have a negative charge. And because of these 2 negative charges in the electrons, what happens is, in an orbital, they start to repel each other. So we're basically having the opposite of when we've got a positive and a negative and they're attracting each other. We've got 2 negatives, so they're actually going to repel each other in their orbital. So we only have 2 electrons per orbital, so 1 pair per orbital. Both have a negative charge, so they repel each other. And how we draw them is we draw them as these half arrows, and we show a spin up and a spin down. So the spin of an electron can either be up or it can be down. For 2 electrons in the same orbital, the spins must be opposite to minimize repulsion. And this is what actually happens. So one will be spinning upwards, one will be spinning downwards, and that's going to minimize the repulsion that's going to be happening. Repulsion is still going to happen because they're both negative charges, but it's going to minimize that repulsion. So you cannot have 2 electrons in an orbital both spinning up, for example. So we represent the electrons by arrows pointing up for spin up or pointing down for spin down to show the different directions of spin. So basically you cannot get, if if we drew it like this, we could not get electrons that were spinning like this. So where they're both spinning up, it just doesn't happen. It doesn't work like that. And we'll talk a bit more about the rules of how orbitals fill in a minute, because there's some set rules for how they fill. But this spinning up and spinning down is very important, that they both spin in different directions. So back to energy levels again. Energy levels, thinking about first energy level is that first shell, second energy level, the second shell, and so on. So one type of atomic orbital makes up a subshell. So that's what we've already sort of discussed. The 3p orbitals, so py, x, and z, combine together to make up a p orbital, a p subshell. Each subshell has a different energy level. So our lowest subshell that has the lowest energy is always our s orbitals. So these are always going to be closest to the nucleus. Our highest will be our f orbitals, so they are furthest from the nucleus. And so what happens is the first energy level, we have 1s. So we have our 1s subshell, and that's it. Then we go to our second energy level. So we have our 2s and 2p subshells, and that's it. Go to third energy level, and we have our 3s, 3p, and 3d subshells, and that's it. Then we have our 4s, 4p, 4d, and 4f subshells. Now, this is a really important thing. Our 4s, if you have a look, and I'm going to try and draw a straight line to show this. Our 4s, I haven't drawn that very well, but our 4s subshell is lower in energy than 3d. So 4s will always fill first. And what I mean by that is we end up actually without a full third energy level. So we can have it full, but what I mean by that is we'd have our electrons filling up this one, electrons filling up our level 2, electrons will fill up 3s, 3p, then they'll fill up 4s, then they go back to 3 and fill up 3d, then they'll go to 4p, and I'll explain that a little bit more in a minute. This is just one of those rules that we have to learn, that 3d has a higher energy than 4s, so 4s will always fill first. So, electron configuration. So we've got shells, we've got subshells, and they are filled with electrons according to a set of rules. So like I was just saying there about the 4s and 3d, there's some rules that we have to follow. So atomic orbitals with the same energy are occupied individually first before pairing. So what we mean by that is, for example, we have 3 sets of p orbitals. We would have 1 electron in px, 1 in py, and 1 in pz before px would have 2 electrons in it. So if we were drawing the p orbitals like this, I'm going to draw them as boxes. Pretend we filled up our s orbitals already. If we'd only got 4 electrons to fill up in this subshell, we would have electron, 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 and then an electron coming in here. What we wouldn't have is what I'm going to draw you here. We wouldn't have this happening, because that isn't following our first rule. So our first rule is atomic orbitals with the same energy. These are all p orbitals, so they all have the same energy, are occupied individually first before pairing. The reason that happens is just because of the charges. Because they repel anyway, we want to actually fill them up individually first before pairing them off together. So that's the first really important rule when we are looking at electron configuration. Our second rule, the lowest available energy level is filled first, and it has to be filled fully unless we are talking about here, and let's pop that bit on, unless we are talking about here 4s and 3d. 4s will fill first before 3d. But again, our 1s needs to be full with 2 in it. Our 2s would need to be full with 2 in it before we can even start to look at 2p. So that's the idea. We're filling everything up full first before we move on to the next one. And like we said quite a few times now, no more than 2 electrons can fill an atomic orbital. So when I was drawing those boxes before, drawing the electrons in with their spin, each box represents 1 orbital. So we have this electron configuration equation. So n is our principal quantum number, so which energy level, which energy shell it is. X would be our type of orbital. Is it s orbital, p, d, or f? And y is our number of electrons in the orbitals of a subshell. So for example, we could have 1, s2, which means our 1 is our principal quantum number. It's the first energy level, our first shell. S is the type of orbital, and then just a little 2, number of electrons in the orbital of a subshell. So that means that S subshell holds 2 electrons. We could also have this, so then we could have 2s2, and we could have 2p3. So energy level 1, principal quantum number 1, subshell S, orbital S, 2 electrons in the subshell. Energy level 2 this time, s orbital, 2 electrons in the orbital of that subshell. Still on energy level 2, but actually now we're on p orbital, so we've changed the orbital, so this actually has slightly higher energy level than our s orbital, and this time we've got 3 electrons in that orbital. So that's sort of what this notation means. So, electron configurations, we can simplify them and we can make them quite complicated. So electron configuration of a whole atom is basically, we would just find out how many electrons are in there and we assign them to each orbital. So for example, we've got potassium here. We know potassium has 19 electrons in it. So we assign all 19 electrons to each energy level as we go. So 1s2, we fill, then we go up to the next energy level. 2s2, that's full, go up to the next orbital. 2p6, that energy level is now full, go up to the third energy level. 3s2, that orbital's full. 3p6, and then remember 4s comes before 3d, so we have 4s1. So that is our full electron configuration when we write out every energy level, every orbital, and how many electrons are in each subshell. We can then use a shorthand version instead. So the shorthand notation is when we use a noble gas that comes before the desired element is written. I was supposed to put that as a separate line. What we do is we write it as the ion, the noble gas is in the square brackets, and then the electrons that come after it are written using general notation. So for example, the noble gas that comes before potassium is argon. So in this situation, we write argon in our square brackets, and then we just show the rest of the electrons that would come after argon. So in this situation, it would only be 1 extra electron, so we have 4s1. So we would just write it like that. What I'm going to do is I'm going to walk you through a couple of examples. These questions come up a lot, and this sort of basically covers everything that we've done so far this afternoon. So you can get asked to write the electron configuration of calcium. The first thing you would be asked to do is to determine the number of electrons in the atom. So we know that the number of electrons in the atom is equal to its atomic number. Its atomic number on the periodic table is 20. So we know that calcium has an number of electrons is 20. Then we're now going to use the rules to fill up the subshells. So we know the first energy level is just made up of 1 subshell. And remember that they go in pairs with opposite spins. So we fill up the first one. So we've got 2 electrons in so far. Then I'm going to get rid of that because that will just start to confuse things. We're going to fill up our second subshell. So the 2s subshell, we've got 4 electrons. Then we can go up to our 2p subshell. And we would fill it up like this. So remembering this time, we haven't paired them up straight away because we have 3 different p orbitals in that subshell. Obviously, we've got 20 electrons overall, so we're only at 2, 4, 5, 6, 7. So we can now go and pair these up to make 8, 9, and 10. Okay, so we're at 3s. We can pair this one up straight away because it's only 1 orbital in the s subshell, and we go to 3p. So we're now at 2, 4, 6, 8, 10, 12. So we have 8 more electrons to fit in. So 3p, fill up our 3p orbitals like this, and then come in and start to pair them up. Now, we have only got 2 more electrons to fit in to get to 20. We do not, as we remembered, go to 3D because 3D has a higher energy level than 4s. So what we would do is we go to 4s, and that would be it. That would be it filled out, showing the spins. So that's the whole written, displayed. So we've determined the number of electrons in the atom. We've used the rules to fill up the subshells. Now, if this would work, we can write the full electron configuration using those subshells that we've just filled up. So our full electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, with no 3d being there because we filled up 4s orbital. We have no more electrons left, so nothing went into 3d, and 3d would have a higher energy level than 4s. Shorthand, the noble gas that comes before calcium is argon. So we would have argon in our Ai in our square brackets, followed by 4s2. And so this can come up for loads of different atoms, and you have to fill them in as you go. It's just sort of a process, remembering it. They'll always write 3D before 4s, but you have to remember that 4s is a lower energy level than 3D. Then, clear all that. Let's have a look at what we would do if we got an ion. So, electron configurations of ions. We would need to write the electron configuration of magnesium 2+. So we would need to determine the number of electrons in the atom. So we know that magnesium, let's get this on, magnesium has 12 electrons. So Mg would equal 12. Now, Mg2+ has lost 2 electrons. So therefore, magnesium 2+ has 10 electrons. So what we're going to do is we're going to go and fill up these subshells exactly the same as we did before. So our rules are we fill them up individually before we start to pair them. We fill up the lowest energy level first, and we fill up all the orbitals together. So we would go 1s, 2s, 2p, 2p, 2p. So on 2, 4, 5, 6, 7, 8, 9, 10, and we would stop there. So our full electron configuration would be 1s2, 2s2, 2p6. Our noble gas that would come before magnesium would be neon, and because this is obviously magnesium 2+, we've lost electrons, we actually don't need to add anything on to the end of neon. So that would be our electron configuration of magnesium 2+. So these sort of questions come up a lot where we need to draw them in showing the spins, we need to write out full electron configuration and do the shorthand. So it's quite a few different skills that we have to put in there, but they're really nice questions. I sort of quite enjoy them and they're quite nice. So the last thing that we'll have a little quick look at today is ionization energy. And this is just a short bit, but sort of looking at ionization energy and understanding the equation for ionization energy. So when we have ionization energy, we always actually have an equation that comes into place. And our first part of the equation that we're going to look at and deal with is, why my mouse isn't working? Here we go, is the electrons. So obviously an ion is where we have lost or gained an electron, but we're going to talk about ionization. So in ionization, we have removed one electron from an atom. So what will happen here is on an ionization equation, we will always have this happening somewhere in our equation. So we will always have an electron being present in our product. So we're going to have electrons and they're going to be present in our product. And this is because we have removed an electron from our reactants from our left-hand side. So we will always have an electron in the products. So we always have an electron term on the right-hand side. So that's the first part that we have to know. I've not drawn this around. So that's the first bit. Second bit we have to know about is the charges. So ionization energy equations, we have to show the charges as well. So every time we do ionization energies, we are talking about an electron being removed. If an electron is being removed, the original atom's charge, so the atom's charge, that's going to increase by 1. So electrons removed, the atom's charge increases by 1. So this would look like this on the equation. So X being whatever our element is, N being our number of charge, and then plus being our positive. So N plus whatever our positive charge is. And then on the other side, we will have X N plus 1 plus. So whatever our charge is on our left-hand side, on the right-hand side, it will have increased at least by 1. We also have to include our state symbols. So state symbols. What happens here is it is always in the gaseous phase when ionization is occurring. So ionization always occurs during the gaseous phase. Therefore, we will always include gaseous state symbols, apart from an electron, because we don't apply electrons, because they're a subatomic particle, we don't apply them to a state. They will just remain the same. So we then get to the full equation that looks a little bit like this. So X N plus G, G goes to E minus plus X N plus 1 plus, and then G again. So for an example, if I was to show you the equation for the first ionization energy of sodium, we would have, instead of X, we would have Na. No charge, because this is our first ionization energy. We've got a neutral atom at the moment. So Na, G for our gaseous state, and we would get our electron, and we would get our Na plus. It's just 1 plus this time at the moment, because we've just gone from neutral to plus, and then we would have our gaseous state symbol. And they would all work in very similar ways. So if we did magnesium, first ionization energy as well, that would look exactly the same like this, but for it being magnesium instead. If it was shown it to be the second ionization energy, we could have magnesium, electron, Mg 2 plus. So only other last little bit to tell you about here is ionization energies. So what we say is the first ionization energy, so let's pop this here. So our first ionization energy, energy produces a unipositive ion. The first ionization energy creates a unipositive ion. It means it has a +1 charge. Therefore, our second ionization energy creates a dipositive ion. So we've got these prefixes again that we were talking about in biology coming in, uni, di, and as you can probably guess, the third ionization energy, ionization energy will produce a tripositive ion. And that's basically, the pattern just goes on and on and on and on. So we would call this whole process the nth ionization energy. So depending on whichever the ionization energy is, depends on what charge ion you get. And that is pretty much it for ionization energies and electron configurations. What, let me just pause this a minute.